welcome to week 2, lecture 1. I hope week 1 went well for you all. In this lecture, we're going to talk about Newton's laws, forces, and mass. This comes from chapter 3, 3-1 through 3-4. And we're going to talk about classical mechanics, Newton's first law, force, mass, and Newton's second law. First off, let's talk about the goal of classical mechanics. If we know the initial conditions, the position and velocity, and the physical properties, the mass and volume of an object, we know or can measure the interactions the object has with the environment. We know or we can measure the interactions the object has with the environment. Classical mechanics then asks, can we predict the subsequent motion of the object? Can we find the position and velocity at all future times? In order to understand the effect of the interactions between an object and its environment, we start by simplifying objects by thinking of them as particles. This is called the particle model, and it just means we can ignore the internal structures of the motion and assume that all parts of the object move the same way. This is useful for learning fundamentals, and then eventually we will analyze extended objects, which you might not always like, honestly. And this picture is a physics joke. It is a spherical cow. Since we treat objects as particles, we can make an assumption when doing some sort of physics problem with a cow. Instead of worrying about all the parts of the cow, we can just imagine the cow as a sphere. And then this SPS here is the Society of Physics Students. It's like a international or national physics kind of club for students at different schools. Okay, let's talk about these interactions between objects and their environments. So first we have an apple. It falls from a tree. The environment is the earth, and the force acting on the apple is gravitational. Then we have a car that comes to a stop. The relevant environment is the road, and the force is frictional. And finally, we have a compass needle. The needle points north. The relevant environment is the earth again, but this time the force is magnetic. So you can see from the table that we describe the interaction of an object with its environment in terms of force. But what the heck is that? Forces are a push or a pull on an object in a specific direction. Force is a vector. In 1D motion, which is where we're starting with this, direction is just given as either negative or positive. Newton's first law of motion says, consider a body on which no net force acts. If the body is at rest, it will remain at rest. If the body is moving with constant velocity, it will continue to do so. Right at the beginning of that, though, it said something. There was a mention of net force. Let's talk about that. So net force is just the vector sum of the forces acting on an object. So here we have our coordinate system set up with the origin in the middle, negative to the left, positive to the right. And we have two forces that are acting on an object. One points to the right, one points to the left. So one is positive and one is negative. And these forces are equal in magnitude because those arrows are the same size. But since they point in opposite directions, the net force, which again is just the vector sum of the forces, equals 0. A momentary diversion to talk about reference frames. Every observer has their own reference frame, so long as they have a coordinate system and are able to measure position, velocity, and acceleration. An example, you are riding in a car. That's you in there. Someone is riding a bike next to the car. and someone else is standing on the sidewalk watching both of you. All three of these people have their own reference frame from which they can observe the environment and take measurements. If the net force on a body is 0, and remember net force is just that vector sum of forces we just looked at, then it's possible to find a set of reference frames where the body has no acceleration. And a reference frame where an object has no acceleration is an inertial reference frame. And Newton's first law is also called the law of inertia, which is why these reference frames are called inertial reference frames. So now let's think about applying the same force to objects of different sizes. We have the car and bike again. Let's say you're trying to push a car with a certain force, and then you try to push a bike with the same force. The bike and the car are going to react differently to the force. The car might barely flinch while the bike starts rolling along. These objects are experiencing the same force, but have different accelerations. This is due to their different masses. Mass is the property of an object that resists change in its motion. The car has a lot more mass than the bike, so it takes a larger force to get it moving. And mass is a fundamental part of an object that doesn't depend on the force applied. Mass is also a scalar quantity, so it doesn't have a direction, and it only has a magnitude. Now, Newton's second law says that the vector sum of the forces acting on an object is equal to the mass of the object times the acceleration of the object. So, vector sum of forces, mass, acceleration. This is true for vector components as well. So for right now, we're just going to be doing these things in one dimension, but that doesn't mean it's always going to be X. Sometimes it's going to be Y because we're going to be thinking vertical instead of horizontal. As of right now, it's not going to be Z, but eventually we'll bring all of these together. Let's do some dimensional analysis to understand the units here. So mass times acceleration has units of mass times length times time to the -2. And because mass times acceleration equals the net force, the force needs to have the same units as mass times acceleration. And this unit is called a Newton. 1 Newton is 1 kilogram meter per second squared. And also, fun fact, a Newton is equivalent to the weight of half a cup of water. I also think maybe it is equivalent to the weight of an apple, but I didn't look that up. So feel free to look it up. And also just something to help you when double checking your units. For me, with these more complicated units that are like a combination of things like mass, length, and time, I just think back to the initial equation. So this is the equation I go back to if I can't remember what Newtons break down into. Because, okay, I know forces in newtons, I know mass is in kilograms, and I know acceleration is meters per second squared. So I can say, okay, that's what a Newton is. So that's something you might want to come back to when we learn other more complicated units. Let's talk through this sample problem to see how to solve force problems. So the question says, a worker, W, pushes a loaded sled whose mass, M, is 240 kilograms for a distance, D, of 2.3 meters over the surface of a frozen lake. The sled moves with negligible friction on the ice. That just means we can ignore friction. The worker exerts a constant horizontal force of 130 newtons as she does so. As she pushes it, I think. If the sled starts from rest, what is its final velocity? So When solving these kinds of problems, the first thing to do is to select a reasonable inertial reference frame and pick the coordinate axes, which right now really just means to find the positive and negative directions. Our reference frame is just going to be an observer standing near the sled. An example of a bad choice of a reference frame would be the frame of the sled itself. Since the sled likely is experiencing acceleration, that reference frame would not be inertial and would not be useful for solving the problem. And then our coordinate axes, we will set the origin to be the starting point of the sled. And then positive will be to the right, and negative will be to the left. Next, we want to draw a free body diagram for each object showing the magnitude and direction of each force acting on it. So that's what we have down here. And just note, this is actually a partial free body diagram because we're only looking at forces in the x direction. There are forces acting in the y direction, but we're starting out one direction at a time, not the band. Anyway, so we have our object indicated by a dot, because remember, we really like to simplify things, that spherical cow. And then we have our vector here, pointing in the direction of the force that the worker is applying to the sled. And then the next part is we also want to label each force with two subscripts. So the object and the actor. So we have the force on the sled by the worker is F sub SW. So force on the sled by the worker. Then we find the vector sum of the forces acting on the object. So the vector sum of the forces is just the force of the sled by the worker. That was the only force in the x direction. And that's also because we could ignore friction, because otherwise friction would act in that direction. From Newton's second law, we also know that the sum of forces is equal to the mass times the acceleration. So we can set those equal to each other because they're both equal to the same thing on this side. So we have the force of on the sled from the worker equals mass of the sled times the acceleration of the sled. So now we can solve for the acceleration because we know the force applied and the mass, they're given in the problem. So we can solve for the one thing we don't know, which is acceleration. We have to just rearrange this equation. So we get that the acceleration is equal to the force divided by the mass, which is 130 newtons divided by 240 kilograms. And that gives us an acceleration of 0.54 meters per second squared. Now we can combine forces with kinematics equations to find the velocity of the sled after it travels 2.3 meters. And technically we already did the forces part because we already found the acceleration, but that's the forces part. So we'll use this kinematics equation here because it's the only one without time in it and we don't know the time. So we have our knowns. Initial velocity is 0 meters per second. The acceleration is 0.54 meters per second squared. The displacement is the final position minus the initial position. The final position is that 2.3 meters. And the initial position is just 0. We set the initial position to be the origin. So the displacement is 2.3 meters. And then we can plug that into our equation. Sorry, look one line at a time here. So the final velocity squared is equal to the initial velocity squared, which is 0, plus 2 times the acceleration times the displacement. And so we get 2.484 meters per second, whole thing squared, but we need to take the square root of that. So that gives us 1.6 meters per second as the final velocity of the sled. Okay, that is all for lecture 1. Have a great day, and we will continue learning more about this stuff in the next lecture.